Today I want to talk about consensus. First, a few seconds of respect for the Ukrainians who are fighting for their freedom still, and for ours. Today I want to talk about probably the most important algorithm for distributed systems. It's called consensus. And here in this algorithm, the nodes have to agree. They all have to agree. You can see that's hard even in real life, huh? So every node proposes a value, and they all have to agree on one of these values. This is a key problem. This is maybe the most important algorithm in distributed systems. We already saw a little bit of that. Total order broadcast, also known as atomic broadcast. Commit, which has to be atomic, distributed databases. Okay, and another one we'll see, which is called terminating reliable broadcast. This is knowing when the reliable broadcast is finished. That's very hard, knowing when it's done. Many tools on the internet use consensus inside all the big applications, Google, Facebook, Amazon. They're all doing consensus, databases, block managers, orchestration, when tasks are moved around, tools in the cloud. They're all doing consensus inside, but they won't tell you what they are doing. What I say is that consensus, you can do what's called heavy lifting. It's a strong algorithm that really can do something for you. Okay? So today we're going to start talking about consensus, but not stop. There's many things to say. First of all, the definition of the algorithm. This has four properties: validity, agreement, termination, integrity. As usual, these will be either safety or liveness. So validity, any value decided is a value that was proposed. They can't just pick some random number. Agreement, no two correct nodes decide differently. They have to decide the same, clearly, otherwise it's not agreement. Also termination. Every correct node eventually will decide. It can't just not decide. It has to decide. And integrity means it decides at most once. So it decides at most once. They all decide the same, and they only decide on something that was proposed. So this is boxing the algorithm. This is defining the algorithm. Okay? So here is a sample execution. 3 nodes, P0, P1, P2, P3. This P0, P1 proposes 0, P2 proposes 1, P3 proposes 0 also. They run the algorithm, and then they decide. You see, each node will decide. So P1 decides on 0, P2 decides on 1, and then crashes. And P3 decides on 0. So is this satisfying the definition we just saw? What do you think? Is this satisfying the definition we just saw? What does agreement say here? Does this satisfy what we just saw? Yes or no? So is it satisfying all these properties? So they're deciding 0 or 1, so that's good for validity. Each correct node eventually decides. That's good. A node decides at most once. Yes. An agreement. No two correct nodes decide differently. So what's a correct node? A correct node is a node that does not fail. Okay. So, does this satisfy consensus? Yes. Because P2 is not a correct node, so what it decides doesn't matter. Okay? So this satisfies consensus. No two correct nodes decide differently. So you can see the failed node is a joker here. Right? We don't care about the failed node. Now, remember, for reliable broadcast, we had a uniform version. And in the uniform version, we did care about failed nodes. Here also is a uniform version. Uniform consensus. Here we care about failed nodes. It's almost the same as regular consensus, except agreement is different. Instead of no correct nodes deciding differently, it's no any two nodes decide differently. So if the nodes decide, even if they fail, it has to be the same. So again, this time we care about the failed nodes. So that's what uniform means. Uniform means that the failed and the correct nodes are somehow in the same basket. They're uniform. We care about that. So what about this execution? The same one as before. Does this satisfy uniform consensus? What do you think? Remember, agreement is no two nodes decide differently. Does this one satisfy uniform consensus? Yes or no? I want one bit of information from you guys. It's not much, huh?
No.
No. Why not? Now I want more. I want an explanation. Yeah, sorry. I want an explanation too. Why not?
Because P2 decides differently than the others.
Right. P2 decides and then crashes. So, but it decides. Even though it's not a correct node, it has decided. And the uniform, we also care about the failed nodes. So P2 is a failed node, but in the uniform algorithm, we care about failed nodes. So this is not satisfying uniform consensus. It is satisfying regular consensus. Okay, so let's make some code. So we're going to write some algorithms for this, starting with a simple, a straightforward algorithm that uses a perfect failure detector, and then we will move to eventually perfect, as usual. That's hard, okay? For consensus, eventually perfect is hard. We will see that we will have to be doing some thinking. So here's the interface. There is a single request, propose, go down, and an indication, decide, coming up. So all the nodes propose, and then they all decide, okay? That's how it works, because that's the four properties, huh? Okay, so let's start in the usual way with perfect failure detector. So this is the easiest algorithm, huh? The perfect failure detector is giving us lots of information, huh? So this one is not yet the internet version, huh? This is not yet the one used by Google and so on, huh? Because that one is harder. That one is actually one of the first really hard distributed algorithms to do. We will see. Let's start with the first one. So we're using perfect failure detector and also the best effort broadcast, our trusty best effort broadcast. So the algorithm is going to be kind of straightforward. So each node has a local variable called proposal, and this variable, it can change it. So it's what it thinks it's going to decide on, but it might change that, okay? So while the algorithm is running, somehow all the nodes, eventually they will come to the same value, okay? So the algorithm works like this. It runs in rounds. So in each round, the rounds are numbered from 1 to n. So there's n nodes, huh? In each round, all of the nodes do something, and then they move to the next round. And then we'll see how that works. Even though they're not actually synchronized, they will know, you'll see how, that they will have to go to the next round. So in each round, round 1, in round 1, there's a node that's the leader. Node 1 is the leader in round 1, and it broadcasts its proposal. It says, V is your favorite. And it decides V. I say V, I decide V. Okay, the other nodes will receive that and remember it. Or, and if that's all, if node 1 does not crash, then that's it. Then V is the decision. But what if node 1 crashes? Oh, well, we will detect it because of the perfect failure detector. It has decided V, but it crashed. So this is regular consensus, not uniform, so we don't care then about node 1. And then we go to round 2. So each node has a chance to impose its will. And if it doesn't crash, the first node that has that chance will do it. But if it crashes, then it lost its chance and we go to the next round. So that's the idea. See, so this has to go through all n rounds. So the algorithm is not so fast here. It has to go through n rounds. But because of that, it's actually easy to prove that it's correct. Remember, we have to prove this algorithm, concurrent and failure probe. So we go round 1 to n, but we start with 1. And we can prove there must be a first correct leader. Since not all nodes are crashing, there's at least one that doesn't crash. Okay? The lowest numbered one that doesn't crash, that one is going to impose its value, P, let's call it P. It will broadcast V. The best effort broadcast works because P is correct. So you see, there must be a first correct node. That is the crucial property that makes this work. So even if there's lots of failures, there's a lowest numbered correct node. Okay, so that's the idea. But still, it's a little bit subtle. So let me show you here an execution. We have 3 nodes. They're proposing A, B, and C. And here are the 3 rounds. Okay? So we assume the nodes will go from one round to the next. And when we show you the code, I'll show you how each node knows. But they all start in round 1. Okay? And in round 1, P1 will broadcast. Okay? It broadcasts. Okay? It decides A, and it broadcasts A. But let's say it fails. Okay? Well, the failure detector will detect that, and then we move to round 2. Okay? In round 2, P2 is the boss. P2 will decide B. It didn't even get the message yet. It will decide B. It broadcasts B. It doesn't go to A anymore, but it will go to P3. Yeah? Okay? Okay, very good. But now, what can happen? So the B will be received at P3, and P3 will take that as the new proposal. So it overrides the local C, and it becomes B. So now everybody is kind of agreeing on B. But look what can happen. We don't know how long messages take. There might be a message still traveling from node 1 and that arrives later than this one from node 2. And this message from node 1 says the proposal is A and not B. So that's not good. So that's something we have to prevent. Okay? So these messages, these old messages that are traveling in the system, they're coming from previous rounds. They're called orphan messages. It's called an orphan because the originating node has crashed, so it's a message that has no origin, okay? Poor message, has no parents anymore. It's traveling around modally in the network, eventually arriving at P3, very late. So it's a message that was broadcast in round 1, and slowly, and eventually arriving in round 2. That's perfectly possible. So those messages, we have to ignore them. So that's kind of the main subtlety of this algorithm. We have to ignore the orphan messages. Okay? Because if we don't ignore them, then we have a problem. P3 will decide A, and P2 did not get the A because P1 crashed and somehow the first one did not make it. So P2 decides B, A and B, so we're not good. We're deciding differently. There's no agreement. So we have to ignore those orphan messages. So we have to be careful. We have to only adopt a message from a node sometimes. So if it's coming from an old round, then we don't adopt it. And that's why we have this local variable called last proposal, okay, last prop. If we get a message which is older than this last prop, then we will ignore it, okay? So we only adopt a message on this condition. So here we're in round 2, and so the last prop is 2. This one is coming from round 1, so which is less than 2, so we don't adopt. So that's how we can ignore these messages. Each message is piggybacked with the round it's coming from, and we know which round we're in. Okay? Okay. Okay, so the idea is the following. The leader in round R, so it starts with 1, but at some point round R is the leader, it crashes. But it still has sent messages, and some of those messages will affect nodes much later on, in a round greater than R. And the way to get around this is to rank the nodes. Okay? So let's say P1 is ranked higher than P2, is ranked higher than P3, and we only adopt if the proposer is ranked lower than last prop, which means it doesn't come from an older round. It's a higher ranked, that means it's coming from an earlier one. Okay? So that's what we have to do. Okay? So here, for example, we take an example with 3 nodes. Decide A, okay, and this is round 1. Propose P1 broadcasts A, and notice each of the other 2 nodes, it knows when to go to round 2. There's 2 possibilities. Either it gets a message from node 1, P1, or it gets a crash indication from P1. That means in either of those 2 conditions, it jumps to round 2. Okay? So the A's here are accepted. The last proposal is 1. And then P2 goes to round 2. And then it's the boss. But the value is now A. It's the same as P1. And it decides A and it broadcasts A. Fine. So it broadcasts A. So the 1 and 2 are agreeing. So the A is also received at P3. And then they go to round 3. So it's basically P3 receives this message, and that's the trigger that makes it go to round 3. And then it decides what its local proposal is, and it's also A. See, because there's no failures here, so the A from P1 has propagated. Okay? So here's another execution with a failure. So P1 now decides A, but then fails. But it has broadcast some things. So that's the funny thing about best ever broadcast. We don't know which of those A's arrive. Any of them might arrive. Okay? So it has to work in all cases. Okay, so the one, it arrives at P3, okay, and then the nodes go to round 2. So P3 knows to go to round 2 because it receives this. How does P2 know that it has to go to round 2? How does it know that? It gets a divine inspiration, and it says, now I'm in round 2. How does it know? What do you think? How does P2 know that it has to go to round 2? It's because of Because of?
Next round.
Well, how does P2 know? What is it needs to get some information. And how does it get the information?
We're right. You want to do it in the queue. No PQ.
Sorry, how does P2 know?
Because you have ranking.
Yeah, but how does it know that at some point that now it's the time to switch? How come it knows? There's somehow it gets some information. What information is it getting? Which I have not drawn here, but there is information coming from P1, no?
The maximum bound to send the message.
But how does P2 know? What information does it get? Huh?
Clock,
No clocks. No clocks. No clocks. This is the. But there is something in this algorithm. There's a failure detector. Right? P is working here. So P2, what does it get as information? It gets a crash message event from that it knows that P1 has crashed. The failure detector tells P2 that P1 has crashed because we have a perfect failure detector here, right? This is the nice thing, we have a perfect one. So P2 is knowing, when it gets that information, it knows it has to go to round 2. So P2 will always get some information. Either it gets a message from P1 or it gets a crash event saying that P1 has crashed. So in all cases, it gets information. You see, there's no case where it's staying ignorant. That's the big advantage of a perfect failure detector, that it will give you negative information. It will tell you when something has crashed. That's like negative information. When something has not happened, when P1 stops executing. So it's the failure detector that's making P2 go to the next round. Fine. And then P3 will go to round 3 because of this message. It receives this message from P2, and that's how it knows. Now what if P2 crashes? Well, then P3 would have gotten a crash notification that P2 has crashed. So in all cases, P3 knows when it's time to go to round 3. Yeah? See how it works? So in this case, P2 does not crash. Okay, so this is consensus question. So this algorithm is a consensus algorithm. Question, is it also a uniform consensus algorithm? Who knows? Maybe we're lucky and we have already a uniform algorithm here. Is this doing uniform consensus? Yes or no?
No, because we decide twice.
We don't decide twice, but it's almost right.
No.
It's not uniform consensus. Why not?
P1 decides differently.
Because
P1 decides A and the
one
other.
decides A, yes, and 2 decides B. They're deciding differently. There's no agreement. And the uniform consensus cares about failed nodes. The regular consensus will not look at P1 as a failed node. But uniform consensus looks at P1 and it decided A. And P2 decided B. So this is not uniform consensus. Okay? Not uniform. Okay? Okay, now after all that talk, I will show you code. Okay, so here's the code. And the code, it's basically 2 pages in a large font, so it's not really that complicated. So it uses best effort broadcast and a perfect failure detector. First is the initialization stuff, so the init event. So we have some local variables, the round, the proposal, the last proposed, the node detected, which is going to tell us which nodes have failed. And also there's some variable that you will see, 2 arrays, delivered and broadcast. So we have first a crash event. So this is coming from the perfect failure detector. So when we see that PI has crashed, we add the rank. So each node has a rank, has like a number, right? They're ranked in order. So this is added to the detector setup. So this is telling us what are the crashed nodes. So that's all initialization. Now we look at the actual code. So this is it. This is the code. So we have 4 rules here. First one is propose. Propose is very easy. If the proposal is, this weird symbol is called bottom, that means it's uninitialized, then we set it to feed. Okay, so we initialize the proposal variable to feed. And then we have a condition here to decide, for deciding. Then we have the best effort deliver, so the messages that arrive. So this condition on the deciding is going to broadcast, and this condition is going to deliver the broadcast. And then finally we have a rule that increments the round number. Okay, so how does it work? So let's look at a little bit more in detail. Okay, so first, set the initial proposal unless it has already adopted another node. So if another, see, the C propose, all the nodes execute propose, but not exactly at the same time. Maybe one node has done a propose, and it's already running the algorithm, and it already has broadcast and set the proposal variable to some other value, and then the node will do propose, you see? It's very slow. The proposals are not all done at the same. That means if the proposal variable has already been bound to something, then we're not allowed to change it. That means it's very important, this rule of if proposal is uninitialized. Because it will not overwrite if the item is already running. Okay, so now the second rule here. So there's some conditions in this rule. So first of all, the round number is equal to the rank of self, me. That means I am the boss. My number is the same as the round number. So then I have the right to decide. Okay? Also, I'm only going to broadcast once. So there's a Boolean, broadcast round is false. This is to make sure I only broadcast once. Once I broadcast, I will set it to true. So this rule will only be executed once in the round, for sure. Also, my proposal has to be bound to something. If it's uninitialized, I'm not going to do anything. Okay? I will not do anything. This rule does not apply for uninitialized variables. I have to wait until the variable is bound to something. Then I will decide. So I will decide locally, and I will do BEB broadcast. That means I will tell all the other nodes, I'm the boss, here's the decision. Okay? So you see, these conditions are guaranteeing it's executed only exactly when it has to be. Okay? See how it works? Once per round, if I have a proposal, otherwise it waits. If the proposal is uninitialized, then this rule does not apply. Okay? But once the proposal gets initialized, then the rule will apply. See that? This is a Boolean condition. So whenever things happen, that condition might become true. So when it becomes true, then this rule can be executed. Okay, so if I have the proposal, I trigger. Triggers, it does the rule. So I permanently decide. So I'm the leader, I decide for me. And I tell everyone else with the broadcast what they should decide. Now this BEB broadcast is going to go everywhere. And it's going to arrive. BEB delivered. Now, the rank, the round number, is an argument here. And it's only going to decide if R is greater than last prop. So older messages with lower value rounds are not going to be making any decision. Huh? They're not changing anything. See, this is getting rid of the orphans. Then, if it is recent, I will update my local variable in the other node, and I will update the round number that it comes from. And I will say, yes, I got it. This delivered is actually needed to go to the next round. I got the message. When delivered is true, it means I got a message. And now the final thing is, how do you go to the next round? Well, there's two possibilities. Either a BEB deliver has arrived, so delivered round is true, or the previous node has failed. So round is element of detected. Detected is the failed one. Huh? So, and it will always be one of those two that we'll get. Huh? So this one will always execute because of the perfect failure detector. So we're really taking advantage of this perfect failure detector here. Right? So next round, if delivered, BEB or crashed. Okay, so that's it. That's the whole code. So it's a little bit subtle, but not that subtle. We can actually prove it. We can reason. We will have to look at the four properties and think a little bit to make sure this code is doing the right thing. Okay? Seems to be doing the right thing. Okay, so validity. Validity means that I'm only deciding on a real proposal, not on some random number. Okay? Well, that's pretty easy to see. If you look at the code, whenever I decide, it's either my own proposal or another guy's proposal that I received. So that's fine. Okay? Validity is good. What about integrity? Integrity means you only decide at most once. Well, we know that we can do that, we can prove that too. The rounds are increasing, 1, 2, 3, up to n. And I am only allowed to decide in the round in which I am the leader. So node 3 can only decide in round 3, nowhere else. So that guarantees that node 3 will only decide once, at most once. Okay? So that's fine. Integrity is good. Okay? What about termination? Will the algorithm terminate or will it get stuck? Okay? Well, we have to make sure that the rounds are advancing, that they're actually being incremented and not stopped somewhere. So if the node is correct, it will actually survive until the round that makes it a leader. So there's two sides here. Completeness of the failure detector. So if the previous node crashes, I will know that and I will advance. But if the previous node does not crash, then it does a best effort broadcast and I will get the message and I will advance too. So best effort broadcast will guarantee the messages if the sender is correct. Huh? So you see, in both cases, crash or no crash, that I can advance the round. So the node rounds will always advance up until n. So the algorithm terminates. Okay, what about agreement? So agreement is not that hard. It's a little bit harder than the others. So no two nodes are allowed to decide differently. So we have to look at our code. Okay. Okay. Well, we have to reason a little bit. So we know the rounds are advancing from 1 to n. And some of the nodes will be correct, some will be failed. We'll take a correct leader with the smallest ID, the earliest. Okay? By termination, it will decide V. It will decide. It will run a best effort broadcast. Okay? And the round bounce will get to I, we know that, and it will best effort V, and because it's correct, every correct node will receive that V and adopt it. And once that happens, all the correct nodes are guaranteed to have the same value. Okay? And because of the orphan removal, no older proposals can ever override it. Once the node get the value, they all keep it. That means everything that happens after, all future proposals would have to be V. Okay? See how it works? So we're actually doing some kind of inductive argument here in a compact way, taking correctly the minimum ID. Okay? And then we're basing it on the fact that best effort will give everybody the same value. And then we're done, and they all have the same value. Okay? Okay. How many failures does this algorithm tolerate? We have n nodes. How many failures are tolerated here? What do you think? It's actually a pretty good algorithm. How many failures can it tolerate?
N minus 1.
N minus 1, huh? Exactly. There has to be at least one correct node, okay, for there to be a decision. And so if N minus 1 nodes fail, any of the N minus 1, during the execution, any time, there's going to be still one correct one, and that one will guarantee everything's good. Okay, so this one tolerates N minus 1 failures. So this algorithm is actually a very strong algorithm. The failures can happen at any time. Messages, so when you do best effort broadcast, some messages can get through, some will not get through. Doesn't matter what the pattern is. Old messages, the message travel time can be different. Old messages can hang around for a long time and arrive later. Doesn't matter. Now, of course, if everything's concurrent, all the nodes are running concurrently here. There's no synchronization between them, and it's correct. So this is not bad as an algorithm already. But this is, in fact, the weakest algorithm we're going to show, because it is really built on top of the perfect failure table. Okay. Here's another, to give you another way of looking at this algorithm, let me give you another kind of way of writing it. So we wrote it using events and rules, but still there's like sequencing in this algorithm. We can write it in another way. So here's another way to write this algorithm. This is called control-oriented instead of event-based. So each node, Pi, is running the same code. Okay. This code here. And it's just running this code. And there's a for loop. R goes from 1 to n. And it's doing n iterations of this for loop. And the little I is a constant. So if R is equal to I, that will happen in the round when node I is the leader. So the little I is a constant, whereas R is a variable, a loop variable. So when R is I, then I will do best effort. The best effort is, we write it like this. For all j in 1 to n, I send a value to bj. Okay? And so there's this end. So this for all line is actually the best effort broadcast. And then there's the decide xi. And then, to make it work, we add one new instruction called collect. This is an interesting instruction. Collect message from node. This is a Boolean, okay? Two things can happen. Either it receives a message from node R, and then the result is true. Or it detects that R has crashed, and then the result is false. So this collect is a very interesting instruction. This is what lets us write this code. All the other instructions here are just regular instructions, but collect is an interesting one. It's a synchronization on messages. So the collect will basically wait for two things to happen. It either receives the message, val x prime r, that's the message that was sent from the leader, or it waits for the leader to have failed. And we're guaranteed that one of those two things will always happen. So the collect is basically going to synchronize on the condition that makes us go to the next round. So this is with this interesting instruction, we can write the code like this. Okay? And if we do get the message, then the collect returns true, and it binds x prime and r. It's like pattern matching. So, and then the local proposal will be bound to x prime. Okay? And also, another thing, the collect will drop orphan messages. If it will ignore messages coming from older rounds than R. Okay? So with this new interesting collect instruction, the whole algorithm can be written like this. Okay? So this is a distributed algorithm that's concurrent and fault tolerant. Okay? Based on this very interesting collect instruction. Okay? So that's another way of writing these algorithms. Okay, so this is a consensus. This is our first consensus algorithm. So you can see it's not that hard, but it's still a bit subtle. But this one is based on perfect failure detector still. But it's only doing regular consensus. But we also want to do uniform consensus. So uniform consensus is interesting because we have to worry about the decisions of failed ones. So how do we do that? Well, actually, this control notation, we can change, we just have to change the code here, and we can make the algorithm uniform. So we basically take this decide here, we move it to the very end. So after n rounds, okay? So we put the decide at the end, okay? Then we have a uniform algorithm. Okay? So what happens if a node decides and then crashes? Okay, it decides here. Well, it has already arrived to round n. Okay? That means all the other nodes have already done their work. So there will be agreement. Okay? So what happens if a node decides and crashes? Well, it has already done all this work. See, the thing about uniform algorithms is that one of the techniques to make them work is you have to kind of delay the decision until you know what the decision is going to be, and then you will have agreement, Because if you decide and fail, you're not allowed to decide something else. Okay? That means don't decide too early. You only decide when you're sure that the other ones are going to decide the same thing, in fact. So with this version, the decision is moved very late, so you know what the others will decide the same thing. Okay? So that's uniform. But there's still one thing, a small minor detail. All what we did so far is with perfect failure detectors. Perfect, never making mistakes. What happens if the failure detector makes mistakes? So an inaccurate failure detector. Well, in fact, it doesn't work, unfortunately. That would have been nice, In the course we're going from, we do an algorithm for P, and then we want to make an algorithm for eventually P. And if we get lucky, our algorithm for P will work for eventually P. But unfortunately, no such luck for consensus. Okay? So here, for example, P2 suspects that P1 has failed. That's a mistake, but it's allowed to do that. P3 suspects that P2 has failed. It's also a mistake, but it's allowed to do that. With eventually perfect. It's allowed to make mistakes. So, P1 decides, but P2 thinks that P1 has failed. So P2 will also decide, but on a different value. So P2 thinks that P1 has crashed. So P2 goes here and decides B. So already we have a problem here, huh? Okay? And P3 is thinking that P2 has failed. So P3 will decide A. So we will have A, B, A. So we're bad, huh? Because P2 has erroneously thought that P1 has crashed, so that it was allowed to decide. But it's not allowed to decide. Because P1 has not actually crashed. So you see, in our algorithm, the failure detector is not allowed to make any mistakes, huh? Or else the algorithm goes bad. Okay? So that was with regular consensus, but with uniform consensus, we have similar problem. It doesn't work either. So neither the regular nor the uniform will not work. So here, P2 thinks that P1 has crashed, P3 thinks that P2 has crashed, and P1 thinks that P3 has crashed. All three are mistakes, huh? So P1, okay, thinks that P3 has crashed. P1 decides, propose A, but it goes to P3, then P2 thinks that P1 has crashed, it says this, but P3 then suspects P2, so it gets only the A. So at the end, we have a decide B, A, and A. Okay? So we're ending up with a consensus that only works with perfect failure detection. So the big question, can it be done with something other than perfect? Can it be done with weaker than perfect? And, well, the whole internet depends on this. Can it be done with eventually perfect, for example? Well, yes, it can. We'll break the suspense. But it's not easy. It's really not easy. This time, when the failure detectors can make mistakes, it gets a lot harder. Okay? And it's subtle. But it's important. The whole internet is built on this answering yes to this question. Huh? Okay, so let me stop here on this cliffhanger, and next time we will see how consensus actually works with eventually